Well, in today's tutorial, in problem 3.32, uh, I actually missed a small point. So there are two things that I want to tell you in this additional video. One is about this point that I missed. Let me talk about that first. And the second is about the reaction forces at the supports that many of you have asked me about. So I didn't get time to do that. But let me first talk about the small problem small issue that I missed. So let me draw this. This was the beam. Oops. This was the beam, x-axis, and the tangent. So I think this angle was theta. There was a twist MA here and a twist MB that was applied here. Right. Now, apart from that, there were reactions here, and it was told to us that the reaction forces are only in the normal direction, normal to the beam itself. So the reaction here, we call that RA, and we denoted it as RA Z K cap plus RA Y J cap. Many of you have asked why this form was taken. I will explain that in a moment. Here, there's a reaction force RB, which we had also taken in the same form in the class. But since it's normal, it will have a component normal to the beam here. The beam is not along the x-axis here as it is at A. So here you will have to take a normal component. So let's call that RB normal. So the vector RB would be RB normal times the unit vector in the normal direction. So N plus RBY J cap. So it will have this form. So I had written I think I had written RBZ K cap here. I had written RBZ K cap. I did not notice the fact that here it has to be normal to the beam, and so it should be along the normal. So we calculated the tangent and the normal. So this was the tangent vector which made an angle theta with the x-axis, and this is what we have taken, the normal unit vector. So this is theta, this is 90 minus theta. So this would be 180 degree minus 90 degree minus theta, that is 90 degree minus theta. So this would be 90 degree minus theta. So N would be minus cos 90 degree minus theta I cap plus sine 90 degree minus theta k cap, which gives you minus sine theta I cap plus cos theta j cap. So this is your N, and therefore RB will be minus sine theta I cap plus cos theta j cap into RBN, the magnitude in the normal direction, plus RBY J cap. So this would be your N. This would be the reaction force at this end B, and then you will do force balance, which is RA plus RB equal to 0. So then you get here, let's take RA is this. So let's take the J components first. So you will have RAY, this is the J component, this is the J component, this is another J component, plus RBY, sorry, this is K, this is K. So RAY plus RBY equal to 0. Let's take the I components. I component is only 1. So RBN sine theta is equal to 0. And then let's take the K components, which is RBN sine theta minus of that. No, sorry. K components. These are J components. These are I components. These are K components. So this is RBN cos theta plus RAZ equal to 0. So we get these three equations, from where we get to know that RBN has to be 0. This has to be 0. So this is 0. So RAZ is also 0. So you are only left with these two. This is the only equation that you get from your balance of forces. Now we are taking moments about this point. So this RBN does not matter for the moments. So the moment equations remain as they are, and the rest of the problem holds. Only thing is that the force equations change. I had used RBZ K cap here. That was incorrect. I should use this RBN in N and calculate and do the force balance correctly. I hope you will correct it. The other question that many of you asked is about the choice of the components of RA. Now the support is like this. It's a plate with a hole through which this shaft is passing. So the shaft passes through this thick plate, where this is the Z direction, this is the Y direction, and this is the X direction. Now I have told you that the reaction forces and moments have to be applied in directions in which the displacement is restricted. So what this support does is it does not allow the shaft, this point in the shaft, to move either in the Z direction or in the Y direction, and that's why we need a reaction force along the Z direction and a reaction force along Y direction. It's also told to us that this is frictionless, so that if the shaft wants to rotate inside this hole, there is no restriction. If there was a restriction, then at this end we will also have to apply a moment, internal moment, to take care of the fact that there's friction between the bearing and the shaft. But this is not there because it's a frictionless bearing. Therefore, the only motions that are restricted are Y and Z. The shaft can move in the X direction freely, so there's no reaction force in the X direction, and there's force only in the Y and Z directions. That's why we have taken it in this manner. Here it's the same. The shaft has no restriction to motion in the tangent direction, but it can't move in the normal direction. It cannot move out of the plane. That's what the bearing here is preventing. So you have a force in the normal direction and a force in the Y direction. So I hope you will correct this and do the problem properly.